This is a demonstration to show how to use tools such as FFT to process our experimental data. Since this is a demonstration, I'll not be using an actual experimental signal since we want to compare our process data with ground truth. So we'll first generate a synthetic ground truth and then add noise to it to make it resemble an experimental data. And then we'll proceed forward from there. So to start off, this is the signal I'm going to generate. I'm going to assume that this is my ground truth. This is basically a combination of a sine signal and a cosine signal. The sine signal has a frequency of 100 hertz f1 and the cosine signal has a frequency of 500 hertz. The sine signal has an amplitude of 1 and the cosine signal has an amplitude of 2. So let us look at how this ground truth, how the actual signal looks like. Let us run this section and this is what we get. So this is how the ground truth looks like. So this is the original signal. So this can be a representative of anything. It can represent how maybe pressure variations are happening at a particular point in the flow field. It might be a representative of velocity. It might be a representative of position of an object that you're tracking. It can be anything. And to sense these parameters, we can use different visualization techniques or sensing techniques to actually capture the data. And we'll again end up with a time series signal as we saw before. And but the data that we get from the experiments, they won't be clean like the signal that we see here. They'll be associated with a lot of noise. And in most of the cases in experiments, the noise is Gaussian in nature. What that means is that if we plot the histogram of the noise alone, it will end up having a Gaussian kind of a profile that is centered around zero. And to replicate this noise here, what we are going to do is we are also going to create a Gaussian noise, and that is created by this rand function here. And again, the spread of the Gaussian noise is decided by this noise amplitude. Here I'm going to take a noise amplitude of 1 so that the noise becomes comparable to my signal itself. So let us generate the noise first. And now what we are going to do is that we are going to add this noise to the signal. And let us look at what this looks like. Yeah, now the plot in blue actually shows signal plus the noise added, and this is how typically an experimental signal looks like. It will be associated with a lot of spurious oscillations, and so this is a representative of an experimental signal that we have that we are going to proceed on for the rest of the analysis. We are going to call this the synthetic experimental data right now. Okay, so we'll first start off with doing an FFT over the synthetic experimental data. The reason we are going to do FFT is so that we can identify what are the dominant frequencies associated with our synthetic experimental data. Let us run this part of the code. So so now we have obtained the variation of the Fourier coefficients. So what we have estimated here is, let me just pull up the PPT. So in the previous lecture we saw that we need to estimate these coefficients capital XK, which basically show the projection of my data vector onto the basis functions. So the function FFT in MATLAB essentially does that. It takes in the experimental data, the data vector, and n, which is basically the total number of points in the data vector as input. And then it estimates this capital XK values. Basically, it estimates the Fourier coefficients that corresponds to different basis functions. And this is the plot of how these coefficients vary. And the value of k here again, it varies from 0 to n minus 1. From 0 to n minus 1. Let us look at the value of n. N here is 1000. So basically, the value of k goes from 0 to 999. But to actually interpret it in physical sense, we need to convert this k in terms of frequencies of the waves associated with these. We can actually mathematically show that this can be mapped to minus fs by 2 to plus fs by 2. Fs is basically nothing but the sampling frequency. Here the value of fs is 9990. So that basically means that this spectrum runs from minus 4995 to plus 4995. And if we just look into the spectrum, we can see that there are four dominant peaks actually. Uh, so two are associated with the frequency of 100 hertz and minus 100 hertz, and two at frequencies of 500 hertz and minus 500 hertz. Now, if we just go into the original data from which we created our experimental signal, we'll see that uh, there are two main frequencies, 500 and 100. So again, like if we look into these peaks and if we add up the amplitudes that is associated with 100 hertz and minus 100 hertz, they come close to 1, which is basically the frequency in the original signal, which is basically the amplitude of the frequency in the original signal that had a frequency of 100 hertz. And again, if we add up the amplitude that is associated with the 500 hertz spectrum and the minus 500 hertz frequency, we end up with a value close to 2, which is again the amplitude of the wave that was associated in the original signal with the frequency of 500 hertz. So what has happened here is that the magnitude of xk has been divided between the positive and negative spectrum. Uh, we'll discuss more about this later on, but first let us reconstruct this signal. Since we have already estimated how these Fourier coefficients vary, to reconstruct the signal, all we need to do is that we need to multiply these Fourier coefficients with the basis functions and then sum them all over up. So that is what this function IFFT does. And let us look at how the reconstructed signal compares against the synthetic data. So we can see that the reconstructed signal pretty accurately captures the synthetic experimental data that we had created. And so now we can use this reconstructed signal. We can perform some filtering over this so that we can extract out only the signal and we can remove the noise. So that is going to be the idea. Now to do that, we are going to first plot the power spectral density. So what we had earlier was basically the magnitude of xk, how this magnitude of xk varies for different values of k or how it varies over the frequency space. Now, instead of looking in terms of the xk, let us look in terms of the power that is associated with each values of the frequency. So to get the value of the power associated with each wave, what we are going to do is we are going to multiply xk with its conjugate. And this again can be mathematically shown that the power associated at a particular frequency is basically nothing but xk into conjugate of xk. So once we do that, we basically get this power spectral density. And since I'd already told that the energy is getting distributed here around the positive and negative spectrum, to make more sense out of the data, what we can do is we can transfer all the energy from the negative spectrum into the positive spectrum by basically just multiplying by a factor of 2. And that is what we are doing here. And let us now plot this power spectral density. So now here we see that there are only two peaks, one that is associated with the frequency of 100 hertz and the other that is associated with the frequency of 500 hertz. And these two peaks correspond to the data basically inside our the original signal. So this is basically the basis of extracting out the data from the noise here. So we can see that the energy that is associated with the data signals, which has these 100 and 500 hertz, they are very high. Whereas the energy that is associated with the noise is very, very less. The noise is not even comparable to the actual signal. So this will be the basis of separating out noise from the data. So what we are going to do is we are going to decide a threshold. We are going to say that if the power associated with a particular frequency, if it is greater than 5% of the maximum PSD value, and here the maximum PSD value occurs at 500 hertz, and let's look at the maximum value here. So thing So it's around 2117. So if it is at least 5% of this value, then that signal will be used to reconstruct the filtered signal. If it is not, then we are going to discard that value. And we are going to reconstruct the FFT, reconstruct the signal using FFT now, just based on the dominant modes that have the highest amount of power. So once we do this thresholding, now we can reconstruct the signal. And so this is how the reconstructed signal looks like. The plot basically in the blue. So we can see that this curve compares pretty well with the original, the ground truth signal from which we started off. FFT, using FFT, we have basically filtered out noise from the signal pretty effectively. And this becomes specifically handy when we are estimating the derivatives. In most of our applications, estimating the derivatives of the data signal becomes very important. For example, if we are tracking, say, the position of a flame inside the channel, the flame is continuously moving and we want to track the position, the velocity of the flame. We are going to get the data series of the position of the flame and we need to estimate the derivative so that we can estimate the velocity associated with it. So there are you can always find parameters where parameters of interest where we need to estimate the derivatives of the time series signal, and especially estimation of derivatives becomes highly erroneous when we have a lot of noise in the data. So let us compare the gradient that we estimate from this filtered signal that we got after FFT filtering. And what if we estimate the gradients directly from the synthetic experimental data? So let us run this section of the code. So we can see that the plot here in this orange basically shows the gradient estimated directly from the synthetic experimental data. We can see that it is highly erroneous when compared to the actual ground truth. The ground truth is shown by this dashed line here, dashed line in black. And we can see that the gradient estimated from the filtered signal actually compares quite well with the ground truth data. So FFT has very effectively filtered out the noise from the signal. We can also use other techniques to filter out data from the noise, and we are going to look into three important techniques that are used. One is the moving mean filter, the other is the median filter, and the other one is the Savitsky-Goulet filter. Let us just look into a brief theory of that. So the way the moving mean filter works is that it we first need to choose a window size of a parameter. We need to input a parameter called n to this filter, and basically it creates a window that encloses n points that is centered around the point where we need the filtered value, and then it basically estimates the average of all the data points that is enclosed within that endpoint window. And once it estimates that average, then the filtered value at that point is basically nothing but that computed average. And it does this operation over the entire data series, sliding this window of size in throughout the entire data series, and basically generates a whole new time series of filtered data. So that is what the moving average filter does. And the median filter is very similar, except that here, instead of computing the average of all the data inside that moving window, it estimates the median of those endpoints that is enclosed within that endpoint window. And once it estimates the median, the filtered value is basically nothing but that estimated median. And again, it does this operation over the entire data series at all points and basically generates a whole new series of filtered data points. So, as we can see here that these filters are very effective in removing these spurious oscillations. So, these oscillations get smeared out when we use this moving average filter or median filter, and that's how it tackles noise. The other commonly used filter is the Savitsky-Golay filter. So here, along with the parameter n that we need to, that says the number of points that is enclosed in a moving window, we also need to specify another parameter which is basically the degree of the polynomial. So here what it does is that it basically fits a polynomial of degree p over the points that are inside that endpoint window using the least square fit approximation. And once it has that polynomial approximation, it uses that polynomial approximation to estimate the filtered the data at that the filtered data at that point. And again, it does this operation over all the data points by sliding that moving window. And in each of these moving windows, it estimates the least square fit approximation of polynomial degree p. Estimates that approximation, and then using that approximation estimates the filtered value. Again, it generates a whole new time series of filtered values. So that is how these three filters work. Let us now compare how these filters, how good these filters are in tackling the noise that we generated. So if going back to the code, so here this is a moving average filter, and here I have chosen a window size of 7. Again, this is arbitrary. Like you can choose a different moving the window size and get slightly different results. So let us just run this portion of the code. So we can see that although the signal is fairly captured, it is not doing as good as a job as what FFT filtering actually did. FFT filtering was able to almost match the original signal with a really good level of accuracy, but the moving average filter does not do that good of a job. This Let's run it for the median filter now. Even for the median filter, I have chosen the same size. The window size is still 7. So we observe almost similar results. In fact, at some places we see that the spurious oscillations are not even removed that well by the median filter. So the median filter underperforms even worse than the moving average filter. Although the estimated derivatives are nearly of the same order, the FFT filter did a much better job. Now let us go into the Savitsky-Golay filter. Here the frame size, basically the window size is taken as 21, and the polynomial order is chosen as 5. Again, you can change these parameters to get a slightly different fit. That can obviously be done. But let us just compare how this looks like. We can see that this does a slightly better job than the moving mean filter and the moving average filter. One thing I forgot to mention was that these plots basically represent the gradient, and this is basically the signal. The filtering using FFT was a lot more effective than the SC filter. But what we can do right now is that we can reduce the noise amplitude. We'll just reduce the noise amplitude and see how good these filters were. Earlier, I had a noise amplitude of 1, which was comparable to the amplitude of the signal as well. So let us now reduce that noise. So I'll make this say 0.25, and let us run the code now. Okay, so we have all the plots. Okay, so for the SJ filter, we can see that it has improved a lot. So as I reduce the noise amplitude, the filtering has become a lot more effective. The original signal compares fairly with the filtered signal. The same uh, median filter, again, the quality has slightly improved. But again, there are still spurious oscillations which it has not very effectively removed out. Uh, and almost the same thing can be said even about the moving average filter. It's better than what we were getting when the noise amplitude was very high. Now let us compare with the again with the FFT. So filtering using FFT, we can see that again there is almost a very nice overlap between the original signal and the filtered signal. So this was just a demonstration to show how effective FFT is in actually removing the noise, and this technique is quite often used in separating out data from noise in experiments. One other thing that I wanted to show was the effect of changing the sampling rate. So let us look into that now. So basically, in the previous section, the sampling rate, basically the value of Fs was around 9,990, and our frequencies of interest, the frequencies that we were interested in capturing, were 100 hertz and 500 hertz. So as per the Nyquist criteria, Fs by 2 is much greater than these values. So we would not have any problems in capturing them. But what if we change the sampling rate? What if we sample it at a slightly different rate? Now what we're going to do is we are going to sample every 13th point. Basically, what does that does is it reduces the sampling frequency by a factor of 13. So let us run this portion of the code. So now this is the sample data. The plot that you're seeing in blue dotted lines, so that is the sample data. When we sample it at 1 by 13th of the initial sampling rate. So let us look at what the sampling rate is right now. So, so let us look at the new sampling rate. So this is 768. And we can see that now the Fs sampled by 2, which is basically 768 by 2, is 384. And 384 is basically lesser than 500, with where 500 is one of the frequencies that we are interested to capture. So now, as per the Nyquist criteria, we will not be able to capture this 500 hertz. So let us run FFT on this and see like what is the value that we actually get. So let us run this portion, and we see here that the 100 hertz is still kind of captured, whereas the signal that was initially at 500 hertz, it now got aliased to 264 hertz. And this is the aliasing that we were mentioning when we discussed about the Shannon-Nyquist criteria. Sampling at frequencies lesser than twice the frequency of our interest, then the energy associated with that phenomena will get mapped onto another frequency. So the energy that was associated with 500 hertz here got mapped out to 264 hertz, and that is what happened here. So this is something that we need to keep in mind when we are doing experiments. If we know that we need to capture a particular frequency of oscillations, we should always make sure that our sampling rate is at least 2 times that value. This is a very important thing to note here. Another thing that I wanted to discuss was of spectrograms. So basically, in an FFT curve, if you look into an FFT curve like this, we basically know that there are dominant frequencies in my signal. However, I have no information about when this frequency is happening in my time series data. Now let us look into data series here. So here I have a data series that shows actually pressure variations in a particular chamber, and it shows that there are some pressure fluctuations at a particular frequency over this small period of time, say maybe from around say 1.7 seconds to around 2.2 seconds. And after that, there are not much oscillations in the pressure. And again, this oscillations occur after a period of during the time period from say around 5.3 to say 5.7. So basically here frequencies are occurring periodically. If we do an FFT of this, it will still show us what is a dominant peak. It will still tell us what is the frequency associated with these oscillations, but it will not give us information on when these oscillations are actually happening in my time series. And that can be a very important information here. And that is where spectrogram comes in. So what this spectrogram does is that it basically it again creates a moving window. So it creates a window that encloses say a certain number of points. It performs FFT on that, and then it slides over, and it slides over to over a few number of points, and it does FFT again over that. And similarly, so it completely slides over this entire time series and performs FFT in each window, and then it displays it as a 2D contour basically. And this is what we finally end up with. So here the x-axis is again time axis, and the y-axis is the frequency axis. Here the color, the intensity of the color basically shows how what is the magnitude of that xk vector. So here we can see that in the time period, say from around 1.7 to around 2.2 seconds, these because of these frequencies, there was a very dominant the dominant frequency was around say around 350 hertz, and its magnitude was very high. And again, the same frequency happened after a particular time period that corresponds to these fluctuations. And again, it represents a magnitude in terms of color here. So that is what basically the spectrogram does. It's basically nothing but a moving window FFT. And again, the way of implementing this in MATLAB is pretty easy. So here it directly uses a function called spectrogram. And to this function, the inputs that we need to give is the data signal, whatever we have. The other input that we need to give is the window length, basically the length of the window that I was talking about, where FFT is computed in each window. So that window length, and then the overlap. Overlap basically shows what is the overlap between two consecutive windows. So if I have a window length of 256 and overlap of 250, that basically means between two consecutive windows, the window just moves by 6 data points. That's it. And then NFFT shows the number of points over which FFT is performed inside each window. And then Fs is basically nothing but the sampling rate. Here to illustrate this example, I have taken a very simple signal. It's called as a chirp signal. So let us first look into what this signal is. So let us run the section. I'll just close the other plots. I'll run the section. So here we can see that the frequency actually varies from around 50 hertz to around 500 hertz in around 2 seconds. So basically the amplitude is nearly constant. But the frequency varies from 50 to 500 as we go from 0 to 2 seconds. And now we are going to, our aim is to actually capture this variation. We need a plot that shows that the frequency actually varies from the dominant frequency. It actually evolves from 50 hertz to 500 hertz. And that is exactly what the spectrogram plot also shows. Again, it shows that the here the units is in kilohertz. So here the frequency varies from around 50 hertz when it is around 0 seconds to around 500 hertz as I move to around 2 seconds. So the important thing is that in FFT we get no information about how the dominant frequencies are evolving over time, whereas spectrogram actually gives that information. It actually tells how the dominant frequencies are evolving over time. So this completes the demo video.